Our human world is rich with meaning, conveyed through words and language. But how does a computer, which only understands numbers, grasp these complex ideas? Historically, computers would just see words as isolated text strings, like entries in a dictionary. They didn't understand the relationships or nuances between them. This posed a huge challenge. How could machines process language, translate it, or even respond intelligently, without a deeper understanding of what words truly mean? The answer lies in a brilliant concept called embeddings. Think of them as a special kind of bridge between human language and computer comprehension. At its core, an embedding is simply a numerical representation of a word, a phrase, or even an entire document. It's a list of numbers, also known as a vector. Traditionally, words were treated as distinct, unrelated units. Each word was just a unique label, like cat is different from dog. We could assign each word a unique ID number, like run is 1, jump is 2, and so on. But this doesn't capture any meaning. With simple ID numbers, king and queen might have completely arbitrary, distant values. The computer wouldn't know they are related. This basic numerical mapping completely lacks semantic understanding. It tells us nothing about how words relate to each other in meaning. We need a more sophisticated way to turn words into numbers, one that actually encodes the essence of their meaning and relationships. As humans, we understand words largely through their context. The words that typically appear near dog help define what a dog is. A famous linguistic principle states, "You shall know a word by the company it keeps." This is the fundamental insight behind embeddings. Imagine words living in neighborhoods. Words that mean similar things tend to live in similar contexts, thus in similar neighborhoods. So, words like car and truck often appear in similar sentences. They share many contextual companions. This contextual understanding is precisely what embeddings try to capture. They build a map where proximity means semantic similarity. To achieve this, embeddings use a concept called a vector space. Think of it as a fancy multi-dimensional graph. For simplicity, let's visualize a 2D space, like a standard graph with an x and y axis. Each axis represents a dimension. In reality, these dimensions don't have human understandable labels, but conceptually, each dimension might represent some latent feature or aspect of meaning. Every word, instead of being a discrete label, becomes a point in this vast, multi-dimensional space. For example, dog might be at 0.8, 0.6. This point's coordinates are the numbers in the word's embedding vector. The vector itself is an arrow pointing from the origin to that specific location. So, how do we figure out these precise numerical coordinates for each word? It all starts with a massive amount of text data called a corpus. A computer program, often a neural network, reads through this enormous collection of text sentence by sentence. Its primary task is often to predict a missing word based on its surrounding context, or to predict context words given a central word. Each time it makes a prediction, it compares its guess to the actual word. If it's wrong, it slightly adjusts the numerical vectors of the words involved. Over billions of these predictions and adjustments, the model learns. Words that frequently appear in similar contexts will gradually have their vectors adjusted to be close to each other. The magic of this process is that words with similar meanings end up being located very close to each other in this multi-dimensional space. For instance, king and queen are semantically related, so their vector representations will be very near in the embedding space. Similarly, apple and banana, both fruits, will occupy nearby regions in the space, reflecting their shared meaning. Words like car and truck will naturally cluster together because they share many semantic properties related to vehicles. Conversely, words that are semantically unrelated, like cat and rock, will be located far apart in the embedding space. The incredible part is that these word vectors don't just show proximity. They also allow for meaningful vector arithmetic. Consider a famous example. What happens if you take the vector for king, subtract the vector for man, and then add the vector for woman? Visually, you're performing a series of movements in the embedding space. You start at king, move in the opposite direction of man, then move in the direction of woman. Astonishingly, the resulting point in the embedding space is remarkably close to the vector for queen. This demonstrates captured relationships like man is to king as woman is to queen. This analogy-solving capability highlights how deeply embeddings understand the underlying semantic structure of language. Embeddings aren't just for single words. The same principle can be extended to create vectors for phrases, sentences, and even entire documents. This has powerful applications. For instance, in search engines, embeddings help find documents that are semantically relevant, even if they don't contain exact keywords. Recommendation systems use embeddings to suggest products or content similar to what you've liked by finding items with close vectors. In language translation, embeddings can map words and phrases from one language's space to another, allowing for more natural and accurate conversions. Ultimately, embeddings are a crucial breakthrough. They effectively transform the abstract world of human language into a concrete, measurable form that computers can understand and manipulate, truly bridging the gap.